period of spring mass system and the period of simple pendulum. Here we are going to show the period of spring mass system and the period of simple pendulum. Period is the time used for one complete cycle. The mathematical expression of period for spring mass system and the mathematical expression of period for simple pendulum are not the same. They are not the same. Generally, period is the time used for one cycle. For example, the spring mass system is moving up, down, oscillates up and down. But simple pendulum oscillates here and there, and it completes one cycle. Simple pendulum and the spring mass system has its own time to complete one cycle. That is said to be period. So, period of spring mass system is mathematically expressed under this lesson. So, look, this spring mass system. Mass is attached to the spring, and this is the equilibrium position. The distance from the equilibrium position, and this point is extension, that is symbolized by x, displacement. The spring moves down, extend, and returns back. It is compressed. When the spring is moving down, there is a restoring force of the spring that moves, that acts upward, that opposes the motion of the spring. But when the spring is moving upward, the restoring force is down. Always, the direction of displacement and the direction of restoring force are in the opposite direction. Direction of displacement and the direction of restoring force acts in the opposite. They are in the opposite direction always. So, from Hooke's law, restoring force, F restoring is directly proportional to extension, the negative of extension. This negative sign shows that the direction of force, restoring force, and the displacement are in the opposite direction. From this expression or relation, restoring force is equal to minus k times x. This is Hooke's law. Minus k is the spring constant. The value of k is different from material to material. That means the materials from which the spring made can affect the value of k times extension. Another, from Newton's second law, force is equals to mass times acceleration. This is the weight of the mass. Mass times acceleration. So, restoring force and the weight is downward and the restoring force is upward. So, since they act in the opposite direction, the two forces are equal in magnitude and they are opposite in direction. Because of this force, restoring force, is equal to mass times acceleration. This expression is equal to ma. Therefore, ma from these two equations, and you combine equation 2 with equation 1, mass times acceleration is equals to minus k times x. From this, we have acceleration is equals to minus k times x over mass. Therefore, acceleration is directly proportional to displacement or extension, but the direction of acceleration and the direction of displacement are opposite. They are opposite. The other point is acceleration is change. The rate of change in velocity is acceleration. Therefore, change in velocity over change in time is equals to the derivative of velocity with respect to time is equals to acceleration. But x, that is displacement, x is equals to a sine of omega t. This is expression for displacement, expression for x. Simple harmonic motion, since it repeats itself at a regular interval of time, it is expressed by sine function or cosine function. So x is equals to a sine omega t is displacement expression or mathematical expression for displacement. But from this, velocity is equals to change in displacement over change in time. If we substitute this expression instead of x, this is equal to the derivative of x with respect to time. So substitute this instead of x and derivate. Finally, the velocity for simple harmonic motion is equals to d by dt of a sine omega t is substituted instead of x. A is constant. Amplitude, that is amplitude. The derivative of sine is cosine omega t, and the derivative of inner function sine omega t, the inner function is omega t. When omega t is derivative in terms of time, it is simply equal to omega. Therefore, velocity is equal to a omega cos omega t. Velocity is equal to a omega cos omega t. Here, acceleration is the derivative of velocity with respect to time. Substitute this expression instead of velocity and derivate to get acceleration, the mathematical expression for acceleration in simple harmonic motion. Therefore, acceleration is equals to d by dt of this expression a omega cos omega t. So a is constant, omega is also constant. The derivative of sine cosine is minus sine. Here minus sine, here minus is used here, times sine omega t. The derivative of inner function omega t in terms of time is, again, it is omega. So this is equal to omega times omega is omega square minus omega square minus omega square a sine omega t is equals to acceleration. A sine omega t is equal to a. A sine omega t means a sine omega t is equal to x. So substitute x instead of a sine omega t. Acceleration, finally, acceleration is equal to minus omega square. A sine omega t can be substituted by displacement. This is acceleration for simple harmonic motion. So acceleration is equal to minus kx over m. Acceleration is equal to minus omega square times x. It is possible to combine this equation and this equation. This is acceleration. This expression is also equal to acceleration. Therefore, from these two equations, we should have minus omega square x is equals to minus kx over m. X is cancelled both sides. From both sides of the equation, x is cancelled and the minus sign is also cancelled. Therefore, omega square is equals to k over m. But omega is equals to 2 pi over period. For one complete cycle, for example, this is one complete this is r. Let's say this is the length of the string r, and theta theta. If theta is one complete cycle, it is changed to 2 pi. Angular velocity is equal to angular displacement, that is theta over time. This theta, when it's complete one cycle, theta can be changed to 2 pi, and the t, small t, is changed to capital T. Capital T is period. The period is time used for one cycle, and instead of angular displacement theta, 2 pi is substituted because we are talking about one cycle, one complete cycle. Therefore, 2 pi over period can be substituted instead of omega. So 2 pi square over period square means 4 pi square over period square is equals to k over m. From this by cross multiplication, period square is equals to 4 pi square over m times m over k. So period is equals to square root of 4 pi square m over k. This is equal to 4 pi square means 2 pi times square root of m over k is equals to period for simple pendulum. Therefore, period for spring mass system. Therefore, period is equals to 2 pi square root of mass attached to the spring over spring constant. This is period for spring mass system. Period for spring mass system. So the mathematical expression of period, time used for one cycle for spring mass system is equals to 2 pi times square root of m over k. So period is directly proportional to the square root of the mass of this. It is affected by the mass that is attached to the spring. Period can be affected by mass, and period can be affected by the force, the spring constant k. The material from which the spring made can affect period, and the mass which is attached to the spring is also affected the period of the spring mass system. The period of spring mass system. The other point is about period of simple pendulum. How we can show or how we can mathematically express the period of spring mass, period of simple pendulum. Period of simple pendulum. B, period of simple pendulum. Simple pendulum. This is simple pendulum. Let's say this is simple pendulum. This is the equilibrium position. Equilibrium position. Here this is length of the string, and the mass m is attached to the string. Now, the weight of the mass is perpendicular downward. Let's decompose the weight of the string. This is the weight of the bob of the pendulum, and along the string here, let's say this is weight along y-axis. Let's say this is y-axis, and here weight along x-axis. Look, this weight can be decomposed into weight along y-axis and weight along x-axis. Weight along y-axis has no contribution on the oscillation of the bob of the pendulum. It is perpendicular downward along the string, and this is here there is tension, angle theta here. Here is also angle theta. But omega x is the only force that acts on the bob of the pendulum to oscillates or to return back the bob of the pendulum toward the equilibrium position. It acts towards the equilibrium position. Therefore, there is also another force, that is restoring force. Restoring force and omega x acts on the bob of the pendulum, and they have contribution on the oscillation of the bob of the pendulum. But W of y, or weight along the y-axis, and the tension has no tension of the string has no contribution on the oscillation of the bob of the pendulum. So restoring force produces oscillation. Due to restoring force, the presence of restoring force, oscillation of any oscillating body can be produced, because restoring force always acts in the opposite direction to the motion of the direction of motion. The direction of motion is equal to minus omega x. This omega x, sine of theta here, sine of theta is equals to opposite side. Opposite side is omega x. Let's say omega x over omega, hypotenuse omega. Therefore, omega x force along this axis, let's say this is x-axis, is equal to omega. This is weight. It is not omega. Weight W times sine theta. So this is equal to weight. It can be substituted by mg sine of theta. So substitute mg sine theta instead of omega x. Therefore, restoring force is equals to minus mg times sine of theta. Minus mg times sine of theta. Take this as equation 1. Take this as equation 1. From Newton's second law, force is equals to mass times acceleration. Mass times acceleration can be substituted instead of restoring force. This force and the restoring force are in the opposite direction because of act in the opposite direction, and they are equal in magnitude. Because of this, mass times acceleration can be substituted instead of restoring force. Therefore, mass times acceleration is equals to minus mg times sine of theta. Mass is cancelled both sides. Acceleration is equals to minus g times sine of theta. Minus g times sine of theta. But if this is x, simply this is x, or this is x, this side is x, and this is the length of the string is L. Sine of theta is equals to opposite side, that is x over hypotenuse side L, the length of the string. X over L can be substituted instead of sine theta. Therefore, acceleration is equals to minus g times x over L. Another expression for acceleration is acceleration is equals to minus omega squared times x. This is the derivative. Simply, acceleration is equals to change in velocity over change in time. This is equal to d of velocity with respect to time. This is equal to d squared of displacement with respect to dt squared. Double derivation of displacement with respect to time is equals to acceleration, or the derivation of velocity with respect to time is equals to acceleration. So if x is derivative 2 times x, means x is equals to a sine of omega t. A sine omega t. If this is derivative 2 times in terms of time, acceleration is equals to minus omega squared times x, minus omega squared times x. So substitute this instead of acceleration, because acceleration is equals to this expression and acceleration is equals to this expression. So substituting this expression instead of a implies us minus omega squared x is equals to minus g times x over L. G times x over L. From this, x is cancelled both sides, minus sign is also cancelled. Finally, omega squared is equals to g over L is left. G over L is left. Therefore, period omega is equals to 2 pi over period. 2 pi over period. Use instead of omega, 2 pi over period is square. 2 pi over period, the whole square is equals to g gravity over L. This is 4 pi square over period square is equals to g over L. By crisscross multiplication, period square is equals to 4 pi square L over g. So period is equals to square root of 4 pi square L over g, and period is equals to 2 pi square root of L over g. L over g. Good. Period for spring mass system, simple pendulum, is equal to 2 pi square root of L over g. But period for spring mass system is equals to 2 pi square root of m over k. In spring mass system, mass can affect period. In simple pendulum, there is no mass here. Mass cannot affect period of simple pendulum, because the mass of simple pendulum is considered as a point mass. It is negligible. Because of this, period can simply affect by the length of the string and the gravity, acceleration due to gravity. So, if you use the length of the string and a small point mass, you can simply measure the gravity around your home by using the length of the string, and small mass is attached to the spring and oscillates here and there. You record the period, and finally acceleration due to gravity around your home simply can be calculated by using this expression.